Hello everyone, thanks for joining. My name is Jimmy from Cisco CS SP Infrastructure team supporting our SATA platform. In this section, we'll focus on how to troubleshoot multicast VPN data paths. Okay, let's start. On the first part, we will recap some basic concepts of multicast VPN, especially PMSI. And PMSI, it is also called core tree. On the second part, then we will using the command and output to demo how to check the multicast VPN data path hop by hop. And then we will review two real customer case examples. Let's go to the first part. This is the multicast VPN network, okay? And the traffic for a single multicast flow, the traffic may come from the multicast source and then send into a CE, a customer edge router, and then packet will be sent to the provider network, provider edge router here, ingress PE. And on this ingress PE, the packet will be encapsulated and then will be delivered by a core tree, a PMSI. And then will send to the multiple egress PE. On the egress PE, the packet will be decapsulated and then sent into the CE on remote side and then delivered to multicast receiver. Depend on the profile. Different profile, we may see different kind of PMSI. We may see inclusive PMSI. We may see selective PMSI. And this PMSI may be MP2MP, I mean multi-directional, or it is P2MP, unidirectional. Okay, we'll get more detail on the next slide. On this slide, this is three most common thing PMSI or core tree type. And the first one, it is multi-inclusive PMSI. Because it is inclusive, meaning all those PE of its customer will join this core tree. Okay? And this is preset default tree. It's telling us that even for a PE, even we don't have any interest receiver, we will join this core tree as well. And only when we configure a customer VRF under the multicast mode, then this PE will join to this core tree of this VRF. Okay. And from function point of view, it is just like an ELAN. So any PE that can communicate with other PE in both directional. It's just like a LAN. Okay. And from implementation point of view, this ELAN may be constructed by one single MP2MP instance, or it may be constructed by multiple P2MP tree. Multiple P2MP means unidirectional, okay? But it is full mesh. So multiple full mesh P2MP tree, he can achieve the same function of ELAN. The second one is the SPMSI is selected, and we don't have here, so it is not multidirectional. And the data MTT is a typical one for this kind of core tree. And this core tree is dynamic created. Only when the PE has interest receiver, he will join to this core tree. Okay. And for the third one, it is as PMSI. So it's multi-directional and selective PMSI. And similarly, as only for those PE who had interest receiver, he will join this PMSI. So it is not preset tree. It is dynamic created. So at beginning, if you don't have any PE has any interest receiver, then we will not have any PMSI instance, MS PMSI instance here. Okay, so only when we have only when we have an interest receiver, then it will trigger to create such core tree and then join to this core tree. Okay, and this core tree is per ingress PE, one MP2MP per ingress PE. So in this case, we have one source, and this is one ingress PE. So we have one instance PMSI here, and if we have another source, and then this is another ingress PE, then we have another MP2MP instance here. Okay, so different kind of profile. For one profile, we may have multiple PMSI in one profile. So we will see two most common theme profile. One is row zone based. The other one is partition based. Okay, let's see how it's going on. So this is for row zone based profiles, and it may be GRE encapsulation, or it may be label encapsulation, MLRDP based. Okay, so but it is row zone based. So for this kind of profile, we normally have two PMSI types. Okay, the first one is called the multi-inclusive PMSI. So at beginning, if we do not have any spatial configure, okay, so all the traffic will passing through this default tree, MP2MP or P2MP4 mesh, MI PMSI, okay. So the RP announcement like S-G traffic, hello packet, and S-G join, pin join may passing through this core tree, okay. So let's think about it. So when we have S-G traffic come here, and then this S-G traffic will be sent into all those PE. And for this PE, for example, even I don't have any interest receiver for this S-G, but we still receive a copy of this core tree, of this packet. Okay, so it's really a wasting of network bandwidth, right? So that's why we got another core tree type get into the picture. So this is called data MTT. For data MTT core tree, only when the egress PE have the interest receiver, then this egress PE will join to this core tree, P2MP tree. Okay. So when the traffic coming from this traffic coming as COMG in the ingress PE side, if the traffic volume exceed a threshold, and this threshold is based on the configure, okay, then he will switch over from the default tree and get into the data MDT tree. So the traffic, this service traffic will be delivered by this SPMSI core tree, okay, and then delivered to the multicast receiver. So this will prevent the wasting of the network bandwidth in the provider network, okay. So this is for row zone-based profile. Then let's see the partition-based profile. The partition-based profile is a bit different. It may also have a default tree, but this default tree, it is not MI PMSI. It is MS PMSI. So it is selective. Okay, it is selective PMSI. So this tree, at beginning, if we don't have any interest receiver of those PE, then we will not have this default tree. But whenever we have an interest receiver, like the PE receive S-G join or star-G join, and we have the interest receiver, then this PE, egress PE, will trigger to create such kind of PMSI, MS PMSI, and then we join to this the core tree PMSI. Okay, and this core tree is bidirectional, it's multi-directional. So the traffic may come from the root to the leaf, ingress to egress, right? And the traffic can be from egress P, leaf, to the ingress P as well, in both directional, okay? And for partition profile, we may also have the same data MDT concept as well. So when the traffic coming and the traffic volume exceed the threshold, and depend on the configure, it will also trigger the traffic from switch over from the default tree and then send into the data MDT tree here, okay? And this is P2MP unidirectional traffic, okay? But in addition to this data MDT tree and default partition tree, we have another kind of the other kind of spatial tree for partition profile. It is called control tree, and this control tree is P2MP control tree. It's SMPMSI, okay? So this control tree is only for those auto RP mapping information. Okay, so when the traffic from an RP, for example, from an RP mapping agent, and then send into the ingress PE here, and all the other PE will join to this ingress PE and this P2MP tree. Okay, so that the RP mapping information can be delivered to all the other PE, and the other PE can know the auto RP information. Okay, so we know this concept and all this core tree. So now let's see how to using command to check those behavior, the behavior of this kind of different kind of core tree and data path. The first question is, we know we have different kind of call tree, right? The first question is how we identify a traffic. What is the call tree for a specific traffic type, right? So this is a simple network setup. It is the profile 15 network setup. And we have ingress PE, PE01, and egress PE02, and PO4 is a P router here. And then on this one, we have two kinds of traffic. One is SCOMG traffic, service traffic. And we also have the RP mapping, RP mapping, auto RP mapping information traffic here. Okay, this is RP mapping agents here. Okay, so now let's see how to use command to check the data path and check the call tree. The first command is we can use a short multicast VPN like VRF profile 15, this VRF lane and context. And then we can see this output can tell us the partition MP to MP and the handle is 1F. And then we can see there's a control tree here and the control tree handle is 1E, right? And then we check in an MPLS MLRTP database here. And we can see the 1F is mapping to MP to MP call tree here, okay? And then the 1E is to this entry here, okay? So that's one thing we need to say is this handle, right? And also we call LSMID is only local significant, okay? Only on this router. So on the other router, when we check in this call tree ID actually is different, right? Like this one, we don't have the 1E here. We don't have 1E here. So now we got a question, how to identify a call tree across the network. Then we need to bring out the concept which is called OP value. So basically, for the call tree or LSP, they are identified by OP value. And we may have different kind of OP value, maybe global ID or maybe MDT value. But on this case, it's profile 15. We are based on the OP value is based on a global ID here. So for example, on this one, 1F, the global ID is 15. So we can say, okay, this is a global ID 15 call tree. And then we check in like PO4, it is also a global ID 15 here. And on the PE02, we also see the global ID 15 here as well. And for control tree, this is global ID 2 and global ID 2, global ID 2. Okay, so for the same call tree, the global ID across the network are consistent. So we can use this consistent global ID to check the call tree behavior hop by hop. Okay. So now let's check the data path for SCOMG traffic. Okay, this is service traffic, right? And the SCOMG traffic is coming from the customer network and then get into the ingress PE, and this is VRF space. And then on the provider network, this is global space here. And then when you go to the egress PE, and egress PE will decapsulate, right, and get into the VRF space and send to the remote side here. So now let's check in the first one in the ingress PE. We also call in position PE, okay? So the traffic coming in VRF space, so we check in unread route for this VRF and for this specific SCOMG 225.0.11, right? So we can see for this unread route entry, and we can see the in-cap ID 3 here. And this in-cap ID will hook into LSMID, and this is MLDP database entry here. So from this output, we can see this SCOMG is hooking to a global ID 1 call tree, okay, PMSI. So now we check in the counter behavior to check in the forwarding behavior, and this command is really helpful. We call show unfit VRF profile, and this platform route statistic. So it's checking some statistic counter, and this is platform statistic counter. So it's directly checking the forwarding behavior of the ASIC or NPU. Okay, so on this one, we can see this counter is incrementing. So it's telling us that the ASIC NPU is receiving the SCOMP traffic, okay, that keep receiving because it's incrementing consistently. So the traffic already receiving here. Then we check in show unfit platform in cap ID 3, and we can see this counter is incrementing. So it's telling us that the packet SCOMP traffic has been encapsulated, okay, by this in cap ID 3 here, okay. So after encapsulate, the packet will be encapsulated into a label packet, right? So we need to check in the MLDP database entry and the label forwarding entry. So using these two commands, and that we check in the global ID 1, and we can get the local label 24003 here. And then based on the 24003, we check in the MPLR forwarding entry 24003, and we can see, okay, the op label 24006. Okay, the packet will be encapsulated by the op label here, and the counter is incrementing, is telling us that the packet has been forwarding out, being the MPLS forwarding label packet, right, sending out. So this is ingress PE. Now it will get into the provider level after the encapsulate. So we may have multiple P router in the real customer network, right? In the real provider network. Okay, so let's see how to check hop by hop. So the command is simple. We check in the MLDP entry, and we using the global ID 1 because it is consistent across the network for this core tree. So we check in global ID 1, global ID 1, global ID 1 here, and we can see from the loop. This is from the ingress side, so we can get the local label and we get the op label here, and then on this one on the downstream router, on the P router side, we check in, we can see the local label and op label, right? And this is mapping here. It's mapping here. It's a map. It's match here. And then we go to the packet, get into the egress P here. So we can see the traffic coming 24003, right? Local label, but the op label is unlabeled. It means this label needs to be popped because this is already egress P, right? We need to decapsulate. So now let's get into the egress P here. So when we check, we can use it because this is for packet coming to a label from the global space, right? And it's supposed to be decapsulated into the VRF space. So now we're using this command, the label 24003, we can see some information that this is table ID. And this table ID actually is mapping to, is hooking to a VRF profile 15 here. They are using the table IDs match here, okay? So now the packet gets into the VRF space. So we can use in the reroute, right, for on this VRF, checking the reroute, and we can see that command, this important information is called RPF ID here. And this RPF ID is on the VRF space, and you need to match to the label RPF ID here. So basically, we're using this RPF ID for packet RPF checking here, okay? So now in the VR space, we're using the command show unfit platform raw statistic, and it will tell us that the counter is incrementing. So it's telling us that this SCOMP traffic in the VR space has been forwarding out of the BVI 115. So it's sending out here. So this is egress CE. Okay, so this is the common theme P2MP commands, the P2MP data path checking commands. And then in addition to that, we also have some, commonly used, frequent use command list, like on ingress PE and P router and the egress PE. I will not go through all the command one by one. It is just a command reference. But some of them are really helpful, like between the PECE here, and we can use in asset list. And the asset list has counter, so we can use in the asset list counter to check the packet really coming or not. And on the egress P also is similar. We can use in the because the IP packet, right? So we can use in the asset list to check in the packet has been delivered or not. Okay. So it depends on the interface. It may be L2 interface, or maybe layer 2, or maybe layer 3 interface. So we can use in L2 ACL, or we can use in L3 ACL. Okay. And on the provider on the P router side, it depends on the profile. So if it is some, it's MLTP based or, label forwarding based, because it's label packet, so MPLS packet, so we cannot use an ACL to match that. And then we can enable the flow monitor. We can enable the net flow, and then using the command to check in the net flow, and then to identify for specific SCOMG flow to see the packet arrive at the P router or not, and to see the packet have been forwarding out to the downstream router or not. Okay, so this is net flow. But it's for if the provider is GRE based, right? And then in the provider network, the packet is being forwarded by provider SCOMG, right? So it's IP packet. So we can use the ACL counter to verify the forwarding behavior as well. Okay. Now let's take a look on the MP2MP call tree. Now compared to P2MP call tree, MP2MP, it means we had both directional. So the traffic we may have traffic from the root to leaf direction, and we can also have leaf to root directional. From leaf to root direction, we call upstream, and from root to leaf direction, we call downstream. Okay, and the checking command is the same. We can check in MLDP entry, and we can check in MPL forwarding label entry, right? Forwarding entry. So, but we need to see on this one for upstream direction. You can see we have like the traffic from the leaf to root, and we have a local label here. And this character U, it means it's upstream. So we need to check this guy, the op label 24012, this one. Okay, and we can see this D is for downstream. Okay, and then we come into here, and you can see the local label 24012, right? This incoming label, and then outgoing label 24010, and this is upstream here. And similarly, when the packet arrives at a root, the local label, right, 24010, and then we can see it needs to be paused. And the label needs to be paused beyond decapsulation. Okay, so this is upstream. For downstream, it's similarly. So, but we have character D here, right? And local label and to op label. And then on this downside, we can local label and then op label. And then we arrive at the leaf here, and this is unlabel, right? It's pop. Okay, this is also local label here. Okay, so it's similar. So now let's take a look at real. We will review two real customer case here. And the first case is like this. It is a multicast driven profile 9. And the problem is I put the topology simple. So we see some PE that lost the neighborhood of the pure PE. For example, on this PE, and when we check in shopping VRF neighbor, and we cannot see the pure side like this PE in his neighborhood list. So it's telling us that for some reason, the hello packet from this ingress PE to this egress PE, the hello packet get lost along the data path. So this is a typical problem that we need to check the data path forwarding behavior. So the first step, we need to identify what is the call tree for this hello packet. So it's based on the default tree, right? Its default is a Rosen base. And then we've identified using the command we checked before, and then we see, it is based on the OP value, and the OP value is MDT, this value. Okay, so we check in the call tree for this OP value. Okay, this is not global ID because it's a different profile 9 here. So now we check in from the egress PE to ingress PE hop by hop. And we identify and we find on one P router, P11 here, and we can see, we do see the local label here, but somehow when we check in the MPL forwarding label entry, this guy, and we could not see any output here. So it's telling us that the 24131 for some reason is not programmed into the forwarding table. So this box is the Copley box. So after we do more check, and we found that the multicast PI was not installed on this router. So after we install the multicast PI here, the problem get resolved. But anyway, the key point is to how to check the data path. After we narrow down, check the data path, hop out, we can narrow down to the coupling block, right? Now let's do next case. The next case, it's Rosen GRE based. So it's profile 0 here. And the problem is it's for AutoRP mapping information. So we see all those remote sites, we cannot get the AutoRP mapping information. But when we check in the local site, we can see the AutoRP mapping information, right? So it's telling us that for some reason, those kind of AutoRP mapping packet, right, announcement packet, for some reason could not be delivered across the provider network. And this is profile 0, GRE based. So we know this is telling us that this AutoRP mapping packet actually will be encapsulated. It's based on the spatial S-G we call 224.0.1.40. Okay, so it's telling us that for some reason this S-G traffic couldn't pass in through the provider network, and the S is the mapping agent address here, and destination is 224.0.1.40. Okay, so now we need to check the data path from here to here. Okay, so let's see how by how. So firstly, we got a problems on the local side. So we check in this guy ingress PE here, and we check in the MVPN profile hardware route statistic counter. And that's one thing you need to say. On the old version, the command is called hardware route statistic. But in the newer version, actually we are changing to be platform route statistic counter here. So anyway, where we check in the counter here and on this ingress PE, and we can see the counter is incrementing. So it's telling us that for this S-G traffic, the packet really already reached the ingress PE. But when we check in the egress PE here, and we check in show on VRF route, we even couldn't see the S-G, only star-G here. So it's telling us that the packet do not reach the egress PE. Okay. So now we want to check. Okay, we may need to check from egress PE to ingress PE, hop by hop. Now we face a challenge is for this specific traffic S-G 224.0.140, the traffic rate is very slow, maybe 1 packet per minute. Okay, in the background, on the provider network, the traffic always, normally we have a lot of background traffic, so the counter, so this counter is not easy to check in the slow traffic rate, right, counter. So now we can try to do some testing. So we try to using a pin test. We're doing a pin, and pin 224.0.1.40, and the source address to be mapping agent, but it's a pin packet, not AutoRP packet. But it will follow the same S-G, right? It will follow the same S-G. And then after we do this pin packet, it's very interesting. We found on the egress PE, we can see the S-G after we do the pin. So it's telling us that the pin test packet can pass in through the S-G data path, right? The causally path, including causally path. But somehow, why the AutoRP packet, AutoRP mapping packet cannot pass in through that? So, but the data path should be the same. So it's telling us that the problem may be related with the AutoRP packet, mapping packet, announcement packet, the characteristic, maybe some spatial characteristic of this packet. So it may be packet is corrupted, or maybe the packet has some spatial, like TTL or something like that. So we then do some checking on the mapping agent configure, and we found that the score is 7. So it means the TTL is 7. So it's not big enough for the packet to pass through such a big network. So we suggest to increasing the TTL to the bigger one, the score to be a bigger one, and after that, the problem get resolved. Okay, so that is the root cause. Okay, that's all. Thank you.